Hi, I'm Tomoki in NCHU. Today, I'd like to talk about theoretical and numerical approach to neutron star. This course is composed of 6 movies, and in this first movie, I would like to briefly introduce astronomical objects in our universe. Let's start. Here, I show many objects in our universe. This horizontal axis shows the size of objects, and this vertical axis shows the density of the objects. You can see human here and many kind of stars like neutron star or suns. And there is more bigger objects like galaxy or observable universe or such kind of things. And in small region, we can find atom or quark nucleons. As you can see, these objects rise in very wide parameter space. In terms of size, smaller size is about 10 to the power of minus 10 centimeter. And largest one is about 10 to the power of 30 centimeter. In terms of density, most dense region is about 10 to the power of 20. And less dense region is about 10 to the power of minus 30. So there is many kind of objects in this parameter space. And first, I would like to briefly introduce these objects at first. Let's start with humans. The size of human is about 1 meter. I think some of you are 1.7 meter or 1.5 meter or 2 meters. But in astrophysics, we don't care these detailed numbers. We just focus on order of the size. And from this viewpoint, humans are about 1 meter. Okay, let's zoom out from humans. Here I show Google map of NCHU. The size of NCHU is typically about 1 kilometer or so. And let's zoom out from this NCHU. Then we find Taiwan. The size of Taiwan island is about 400 kilometers. This is much, much bigger than NCHU, but it is still smaller than many other objects in our universe. Okay, let's zoom out more and more. Then we can find our Earth. The radius of Earth is 6,400 kilometers, and mass is about 10 to the power of 25 kilograms. I think you cannot imagine this mass, but what size it is. It is much, much bigger than, for example, us, our humankind, or NCT, but it's still small in our universe, even in solar system. From a viewpoint of observer, we can zoom out more and more. Then we find our suns. The radius of the sun is about 10 to the power of 9 meters, and mass is 10 to the power of 30 kilograms. It's much, much bigger than even our Earth. You can compare these two values and these values. But it is still one of the stars in our universe. When we zoom out from sun, we find solar system. Solar system is composed of many objects. Example is written here: sun, planet, comet, and asteroid. These objects are attracted by sun's gravity. And sun creates this kind of very huge system in the universe. This is already much very, very big, but we can find many other objects. Let's zoom out from solar system. Then we found our nearby star here. This star is called Alpha Centauri. Here is solar system, and Alpha Centauri, the distance to the Alpha Centauri is much larger than the size of our solar system. And the distance is about 1 times 10 to the power of 19 centimeter. It means there is 19 zeros after 1 and centimeter. So far, we see stars in the universe, but it's still very small parameter region in this initial diagrams. Only just this kind of region. And let's move to much bigger systems. When we zoom out from sun or nearby stars, we find our galaxy. I don't read these values, but you can find the size of our galaxy or mass of our galaxy is much, much larger than single stars. Okay, here is one quiz. How many stars in our galaxy? Please consider. One key parameter is its mass. Mass of the galaxy is about 10 to the power of 12 times solar mass. And solar mass is the mass of sun. Using this value, please estimate how many stars in our galaxy. Okay. I think many people choose this value, B, but the number is about 10 to the power of 11. And the mass of star is this about very, very roughly about this value times solar mass. And many parts of our galaxy is dark matter, and we cannot observe these objects directly using electromagnetic waves. So we see this very beautiful structure here, but this is only small portion of total galaxy mass. Okay, let's zoom out from galaxy. When we zoom out from galaxies, we find some group of galaxies. Here is our Milky Way, and many dwarf galaxies are here, and we can find nearby galaxies, Andromeda Galaxy, and as you can see, around galaxy we find this kind of structures, group of galaxy. This initial group is called local galactic group, and it is composed of about 50 galaxies. Okay, then let's zoom out from this local group. Then we can find galaxy clusters. This is a kind of structure, but we cannot, This is a kind of structure, and this structure is composed of about 1,000 galaxies. And this is very brief image, but there is some kind of clusters in our universe. And when zoom out more and more, we find supercluster. maybe here is our local group. And this is the plot of galaxies near our galaxies. Not near, but around our galaxies. This cluster is called Laniakea supercluster, and it contains about 4.1 million galaxies. I think you cannot imagine, but this kind of structure is, we can find this kind of structure by observing galaxies around our galaxy. Okay, so our Earth is very small portion of this kind of big structure in the universe. And this is sometimes called large-scale structures. When we observe galaxies and plot the position of galaxies, we find this kind of structures. Here is many galaxies, and here is almost no galaxies, and here is galaxies, and here is no galaxies. This kind of structure is called cosmic web, and it mainly composed of supercluster and filament like this, and void, no star region. And typical size of this structure is about 30 megaparsec. And when we zoom out more and more, we reach the edge of observable universe. And from this edge of observable universe, cosmic microwave background is emitted. And this is a typical image of cosmic microwave background. Okay, so far I showed these structures in the universe. As you already know, the size it ranges from 10 to the power of minus 10 to the 10 to the power of 30. So it is 40 order of magnitude, and density is 10 to the power of 50 order of magnitude. So as physical object, scale of physical objects is in this kind of many orders of magnitude. And we have to be able to estimate where we are or where the physical objects are. Yeah. We have to check this kind of values using physics. This is called a kind of Fermi problem, named after a very famous physicist Enrico Fermi. And this question is well-known Fermi problem in Japanese. I don't know whether this is known in other countries, but this is one good example for Fermi problem. Okay, let's estimate how many piano tuner in Chicago. This is problem. And I think all of you don't know exact value of piano tuners, but using our daily experience, we can estimate this value. This is called the Fermi problem, and this kind of estimate is very important in astrophysical objects because the parameter range very wide regions. Okay, here I show one possible solution for this estimate. From daily life, we know the population of city. In case of Chicago, population is 3 million people. And here we assume some parameters based on our daily life. Let's assume 3% makes one family, and 10% family have piano. From these three assumptions, we can estimate the number of piano in Chicago. This is population, and 3 person makes 1 family. And so this value is the number of families. And using this third assumption, we can estimate a number of piano in Chicago. It's about 10 to the power of 5. Okay, so far we estimate the number of piano. And here's another assumption. Piano is tuned once per year. And here it's about the assumption about the tuners. We don't know detailed numbers, but just assume 1 or 10 or such kind of orders, not focus on detailed values. Let's assume one tuner tunes 3 piano per day, and one tuner works 250 days per day. So using these two values, we can estimate using these values, we can estimate the number of pianos tuned by one tuner per 1 year. Just multiply these values. So one tuner tunes about 700 pianos per year. And using this assumption, we can estimate the number of tuners. Here's number of piano, and here is number of tunes per tuner per year. And using this assumption, just dividing this value by this value, we can estimate the number of tuners in Chicago. It's about 100. This is very, very rough estimate, and not sure whether this is about 10 or 1,000, but we can expect the true value is not so different from these values. This is called Fermi problem. And at last of this course, at the last of this movie, I would like to introduce few example of this kind of problem. Please try it. Okay, here is a summary of my talk. I showed hierarchical structure of the universe. There is many objects. Nucleon, neutron star, sun, human galaxy, universe. From 10 to the power of minus 10 centimeter to 10 to the power of 30 centimeter. And density is from 10 to the power of minus 30 gram per cc to 10 to the power of about 20 gram per cc. So to find the position in this kind of parameters, order estimate is very important, especially in astrophysics. And this kind of order estimate would be useful in our daily life. Just, for example, chatting. Okay, here is for homework of this movie. Using order estimate, please estimate these 4 values. And here is hint, but please try just see this problem at first. You can estimate, I think you can estimate how many watts is a sun per 1 kilogram using its luminosity and mass. In addition, you can estimate how many watts is a human per 1 kilogram. So using these two calculations, we can compare watts per mass for human and suns. This is very interesting problem, and please try at least these 2 questions. And here is another problem, and please try it. Okay, I would like to finish this movie. Thank you very much.